Welcome again, everyone. In this video, we will look into the similarities and differences between a tradition computer like the desktop or a laptop and an edge device. We all know how a desktop or a laptop looks like, and you're probably watching this video on one of them. But do you know how an edge device looks like? Well, it's just a printed circuit board with lots of devices attached to it, and there are tons of them out there. Here, I have shown three that are super popular among the edge device and the IoT community: an Arduino Nano, an OpenMV Cam H7 Plus, and a Raspberry Pi 4. And we will discuss them in a little more detail in later videos in this section. Coming back, now that we know what an edge device looks like, let's compare it with a traditional computer. A computer, whether it's a desktop or a laptop, is a general-purpose machine designed to perform multiple tasks like making presentations, coding, playing games, watching videos, or just browsing the internet. And because of these large variety of tasks, its specifications are highly configurable. If you wanted to play video games, you would probably add a super fast CPU and a GPU. If you wanted to make videos, you would probably want a large hard disk to store all those videos. Or if you wanted to multitask or do office work that required the use of multiple applications, you would want to add more RAM, etc. An edge device, on the other hand, is a specialized piece of hardware designed to do one specific task, and it thus has a very limited flexibility in design. You cannot change the processor or the RAM or the storage on an edge device, though some devices may allow you to add external devices to supplement these capabilities. For example, Amazon Alexa is designed to take an audio input, process it, and then output a response again in audio format. It thus has at its core an edge device with a microphone, a Wi-Fi module, and a speaker. If you wanted it to take pictures of your dog and share it over social media, it wouldn't be able to do that, at least not without redesigning the complete application, both the hardware and the software part. Similarly, for your smart doorbell, or the automatic car parking meter at your neighborhood mall. Your doorbell cannot measure the temperature or pressure of your surroundings or take CO2 readings, and the parking meter cannot do what Alexa does. If you wanted that, again, you would have to redesign, but you couldn't do it off the bat. Let's now compare them from a hardware perspective. Most modern-day computers have a compute speed between 2 and 5 gigahertz, a RAM between 2 and 64 gigabytes, and a hard disk space between 250 gigabytes and 4 terabytes. They will also consume power between 40 and 200 watts. An edge device, on the other hand, has a compute speed between 4 and 400 megahertz, a RAM between 2 and 512 kilobyte, a flash storage between 32 kilobyte and 16 megabyte, and will consume anywhere from 120 microwatts at standby to 40 milliwatts when at full capacity. As you can see from these numbers, an edge device is severely constrained in all these four parameters as compared to a traditional computer. The difference in RAM and storage numbers is particularly huge, with RAM being 125,000 times smaller on average, and storage being 250,000 times smaller. And this is really because we want the edge device to be smallest size possible and consume the least amount of power. If your smartwatch or smart glasses weren't sleek in design or required a change of battery every 2 weeks, they wouldn't be so cool now, would they? Finally, let's also look at a computer and an edge device from a software stack perspective. Broadly speaking, a computer has two parts: the hardware and the software. The hardware is the actual CPU, GPU, and other devices, including peripherals like the mouse and the keyboard. The software is the lines of code that help you perform the function that you want to do on a computer, as well as interact seamlessly with the different devices. This software stack sits on top of the hardware and can itself be divided into three components: the operating system, the libraries, and the applications. The lowermost part of the software stack, the operating system, in itself has multiple pieces of code that look after stuff like process management, memory management, network management, input and output device management, to name a few. This last one, the input and output device management, is the part that interacts with your hardware, like the keyboard, mouse, external monitors, etc. On top of the operating system are lines of code called libraries. The libraries contain code like frameworks for graphics or network operations that help in developing applications by providing pre-written code to perform common tasks. And finally, the application layer represents the actual software applications run by users, such as word processors, games, or data analysis tools. In a desktop or laptop, these layers are usually more complex, supporting powerful applications with extensive functionality. In contrast, an edge device, which operates on a microcontroller unit or an MCU, typically has simpler, more specialized software and libraries, optimized for specific tasks like sensor data processing and basic device control. In fact, in many edge devices, there is little to no operating system. This simplification in software is crucial for operating within the limited processing power and memory space of MCUs, which are common in edge devices for tasks like real-time data processing, close to the data source or the edge of the network. This setup also minimizes latency and reduces the load on main network resources, which is crucial for efficient real-time operations. Hope this video provided you with some tangible points of difference between a traditional computer and an edge device. In the next few videos, we will take a deep dive into edge devices and discuss its various components and communication protocols. See you there. Welcome back. In this video, we will look at some of the components that make up the edge universe. One device which is extremely popular in the Edge ML community is the Arduino Nano 33 BLE Sense development board. This is because it checks a lot of the boxes for an ideal edge device, like small size, low power consumption, lots of internal sensors, connectivity to other devices through Bluetooth, etc. We will discuss the factors that are important to consider when deciding on an edge device, as well as the Arduino Nano 33 in later videos. But let's first get acclimatized to an edge device. This is what an edge device typically looks like. It will have a microcontroller unit, or MCU, along with a network module to connect with the outside world, like Wi-Fi or Bluetooth. This one has a Bluetooth Low Energy, or BLE module, which, as the name suggests, uses less energy, and this is pretty standard these days. Another thing that a development board will have is some sort of USB connection to connect to a computer, so that you can write a program on the computer and transfer it to the edge device. The USB also provides power to the edge device, though you can power the device using an external power source, like a battery or a power bank as well. Another thing to note here is that though development boards have USBs, a production device, which is a device actually being used in the real world, may not have a USB port. There are a couple of reasons for this. First, a production device is extremely specific to its task, and its size may not allow for a USB port, which, as you can see, takes some space. Secondly, and more importantly, it may not need a USB port. The code to run may already have been added to the microcontroller unit, and there may already be an external power source powering the edge device and the external input and output devices. The third component to look out for in a device is the reset button, and it does exactly what it says. It helps to reset the device. Let's say you are transferring the program that you wrote from your computer to the device, and the computer and the device get stuck, which will happen sometime. Well, in this case, you can use this button to reset the device. Another thing that you will find on your device are inbuilt or internal sensors and other input and output devices. The sensors can collect the data on which machine learning models can make inference. This device, the Nano 33 BLE Sense, has tons of sensors, like the temperature, pressure, IMU, and the humidity sensor, as well as a microphone, as you can see, but most edge devices won't have this many components on them. Most will usually have just a couple of them, more or less. And so what do you do if the device you want is not built in? Well, you can always connect an external device, and we will spend a lot of time in this course to see how exactly to do that. And that is all for this video. In the next video, we will look at some input devices that are available to us to build our favorite edge applications. See you there. Welcome. In this video, we will dive headfirst into the fascinating world of input devices, which are a key component that enables smarter, automated solutions right where data is created. Let's explore what these different devices are and how they can be used to build applications that can help improve our daily life. Let's start with a simple definition so that we are all on the same page. Input devices are hardware that help gather information from the environment. This information is then processed locally by edge devices to generate insights on which actions can be performed. Pretty straightforward, right? With that out of the way, let's look at some common input devices used in edge AI. Sensors collect data from their environment. This could be temperature, motion, or even humidity. And we just saw a device that has some of these sensors built in. Well, you could add a few more sensors like the particle sensor, which in short generates the AQI reading that you see in your weather apps, and gas sensors for a few different gases like sulfur dioxide or nitrous oxide, and create your own weather station. You could collect data from 10 to 20 such stations every minute or so and build your own weather app. Or you could sell the data to news channels. Because we are interested in edge applications, you could use the data to turn on your fans, your air conditioners, your air purifiers, and open or close doors and windows. Or if you really wanted to go big, you could use the data to build a model to predict energy demand and then use those insights to trade in the energy markets. The possibilities are really endless and only limited by your imagination. Let's look at OBD2 readers now. OBD2 readers are used in vehicles to access the diagnostic system. They tell you what's wrong with your car, and this may be your headlamps or indicator lights, brakes, or airbags. They can also monitor engine health and predict failures. With self-driving cars a few years away at the maximum, starting a company that provides real-time preventive maintenance updates to individual car owners and taxi companies to reduce downtime and improve efficiency could be super rewarding. Next are RFID readers. These devices use radio waves to read and capture information stored on an RFID tag attached to an object. In retail, RFID tags can help manage inventory more effectively by tracking products throughout the store. They can also be used in the transportation and urban planning space to automatically pay parking and highway toll fees. Moving on to barcode scanners. These are optical scanners that can read printed barcodes and convert them into digital data. This device is super popular in the supply chain management space. For example, in a warehouse, employees can use barcode scanners to track shipments and automate parts of the inventory management, reducing errors and speeding up operations. Next, let's come to buttons and switches. Simple yet effective, these can be used to start or stop a device. Buttons help you switch on and off your everyday home appliances, and switches help you switch on and off your lights. In industrial settings, a switch can also be programmed to initiate or end a machine's operational cycle without needing human intervention. Finally, let's take a look at joysticks and keyboards. While typically associated with gaming, in Edge AI, joysticks can control robotic arms to perform tasks like picking up and emptying trash cans into a waste disposal truck. Similarly, in manufacturing, keyboards can input commands quickly at local terminals, thus enhancing productivity in manufacturing processes. In conclusion, input devices are crucial for collecting the data that makes Edge AI work. By combining these different devices with edge computing, we can streamline complex processes, reduce manual labor, and enhance decision-making. Whether it's your car, your house, your workplace, or public infrastructure, these input devices can support edge devices in reshaping how we interact with technology and ultimately make our lives easier. And that is it for input devices. Hope you had fun. In the next video, we will explore the different types of output devices in Edge AI. See you there. Welcome back, everyone. Let's now focus on output devices and see how they can be applied in real-world scenarios. Like before, let's start by defining what an output device is. In the realm of edge machine learning, an output device is a piece of hardware that receives data processed locally on the edge device and then acts upon that data. These devices are crucial for performing real-time actions without needing to rely on cloud computing. Let's now look at some common output devices used in edge computing. LEDs can indicate device status or alerts. For example, a smart smoke detector might use an LED to flash red when smoke is detected by an edge-based sensor, alerting restaurant, building, or factory occupants immediately. Next, let's look at motors. Motors enable physical action. In a smart home, motors could be used to automatically adjust blinds based on sunlight detection, optimizing light usage and energy consumption. In a smart shop or building, motors could be used to open or close doors automatically depending upon the scenario. For example, if robbers were to enter a shop, doors could automatically be shut and sealed. In a waste segregating facility, motors could be used to change the robotic arm's angle to pick up precious items like aluminum cans and other metallic objects. These metallic objects could then be sold separately, while the rest of the trash moved through other segregating mechanisms. Again, the possibilities are endless. Another type of output device is displays. Displays provide visual feedback. In a restaurant, a display could show which food orders are ready to be collected from the counter. At a car manufacturing facility, a display could show the number of cars produced in a particular shift and other production metrics. Remember, the weather station that we talked about in the last video? A display device attached to it could show weather readings in real time to people passing by. Another usage of displays is smart wearables. A wearable device could use a small OLED screen to show real-time health statistics processed locally from sensors monitoring the wearer's vitals. In fact, this is what first-generation smartwatches were, just some sensors and a display screen put together. Let's now understand camera controls. While camera is an input device, camera controls can be seen as output devices, as they can adjust the camera settings automatically based on the insights received from a microcontroller. For example, in security scenarios, edge devices can control camera angles and focus based on movement detection, enhancing safety without human supervision. Along similar lines, camera controls can also be applied to drone cameras covering sporting events like marathon, car, and boat races to get the best shot of athletes. Finally, speakers are used for audible alerts or communication. In steel factories, if the temperature of a furnace is above a certain temperature and a motion is detected beyond the safe travel point, an alarm can be set off, informing the employee or employees that it's unsafe to proceed. Similar applications could also be designed for mines, whether it be coal, silver, copper, or gold, to improve miner safety, and for nuclear reactors, though you may also want to add a radiation sensor there. To summarize, edge machine learning leverages a variety of output devices to enhance efficiency and safety, reduce manual labor, and to improve productivity across different sectors. Hope you enjoyed these discussions on different input and output devices and how they can be applied in the real world. Let us know in the Q&A section. Also, let us know how you plan to use edge machine learning in your local setting. Coming back, all these different input and output devices can't always be built into an edge device. What do you do then? Well, you use pins to connect them to an edge device. In the next couple of videos, we will look at the different type of pins. See you there. Welcome back. In this video, we will explore what pins are and how they can be used to connect external input and output hardware to our edge device. Let's first look at an edge device, and then we will dive into what the different pins are on these devices and understand their roles, types, and connectivity options. The edge device that we are looking at is again the Arduino Nano 33 BLE Sense, and we took this image from their datasheet. Datasheet is a document that contains information about the edge device, like the microcontroller unit it has, the device's memory and storage numbers, the sensors it has and their specifications, its power requirements, its operating temperature range, and much more. The datasheet is used to learn more about the device and see if it fits our application use case. If you are interested, we will attach the datasheets for a few popular devices in the resource section, and you can check them out. Coming back to this diagram is known as the pinouts diagram, or the connector pinouts diagram, and it shows the different pins available on an edge device. Pins are those small metal points on the edge of the device. They are used for connecting the microcontroller to other devices or sensors. Not all pins look the same, though. Some have headers, which are like extending arms that make it easy to attach wires and components. Others are castellated, which means they have notches that allow the pin to be soldered directly to a surface, facilitating smaller and often more permanent installations. There are several different types of pins on an edge device. First, let's talk about the power pins. Power pins are used to supply the power needed from external sources, like batteries or adapters. The ones to look out for are the V-in, 3V3, 5-volt, and ground pins. V-in, as the name suggests, is an input power pin, which is connected to a higher voltage, like 5 to 10 volts. Note that when the power is supplied to the board with this pin, the USB power is disconnected. Also, always remember to give a voltage amount less than the voltage limit to prevent damage to the edge device. Next are the 3V3 and 5-volt pins. These output stable regulated voltages of 3.3 volts and 5 volts and are used to power various external input and output components. And finally, we have the ground pins, which complete the circuit by providing a return path to the power supply. Those were the power pins. Next, we have the digital pins, which are used for digital signals like the on or off states, and are thus perfectly suited for LEDs, switches, or digital sensors. These pins on the right in the diagram, starting with capital D, are the digital pins. There's also D13 on the top left, though that is connected to the inbuilt LED, so it is recommended to not use it for external devices. The pins on the left, starting with the letter capital A, are the analog pins. The A-ref pin is for the reference voltage for analog devices, and we will look at it a little later in this section. For now, just understand that it is used for analog devices. These analog pins, the ones starting with the letter capital A, are used for reading variable signals, or readings from sensors like temperature, humidity, and light. The signal isn't just on or off. For example, a temperature reading can be 10 degrees, 15 degrees, 20 degrees, or for some parts of Asia, even 40 and 45 degrees. They can also be 10.5, 15.2, or 20.75 degrees, and so on, depending upon the resolution of the sensor. These analog values or signals are converted into a digital form for the microcontroller or the processor to read them, using something known as an analog-to-digital converter, or ADC. And we will be discussing ADCs in detail in a separate video right after we finish this discussion on pins. This video has been a little long, so let's do a quick recap. The first type of pin that we discussed were the power pins that are used to power the board and peripheral devices attached to the board, like LEDs, sensors, and switches. The second type of pin that we looked at were the digital pins, which are used to connect to devices which have only two states, either on and off or low and high. In voltage terms, this can be 0 volts for low and 3.3 or 5 volts or VREF of the board that you are using for the high. For our Arduino Nano board, this high is 3.3 volts. This information again is available in the datasheet. Examples of digital devices are LEDs and switches. The final type of pins that we looked at were the analog pins, which are used usually for sensors and other devices like potentiometers. These give back a range of values which are converted into a digital format before being used. There is another type of pin called the PWM pin, which is also marked on a pinout diagram, either separately or by using the wave or the tilde signal. For our Arduino board, all the digital pins can double up as PWM pins, and this is why you can see the tilde symbol before each digital pin on this pinout diagram. Let's discuss what this pin is and what is it used for in the next video. See you there. Hello, and welcome to this video on the PWM pin. In this video, we will look into pulse width modulation, commonly known as PWM, and its critical role in computing systems, especially in edge devices. Let's start with an introduction to PWM. PWM is a technique which is used to control the amount of power delivered to an electronic device by breaking up the power signal into distinct parts. Instead of delivering a steady output, PWM rapidly switches the power between fully on and fully off, effectively creating an output analog signal. In the diagram on this slide, we show this for 3 cases. The broken green line denotes the period when the pulse oscillates. So if a signal is 100 Hz, it will oscillate 100 times each second, or the time period for each oscillation will be 0.01 seconds. Now, duty cycle denotes the amount of time in percentage that the power is on in each time period. So if the power is off for the whole of this time period, it is denoted by a 0% duty cycle, as shown in part 1 of the diagram. If the power is on for 50% of time and off for the rest, it becomes a 50% duty cycle, and the effective output voltage becomes 2.5 volts if the reference voltage is 5 volts, or 1.65 volts if the reference voltage is 3.3 volts, like for Arduino Nano. Similarly, for a 100% duty cycle, the power would be on all the time as shown, and the effective output voltage would simply be 3.3 volts and 5 volts. And so, you can create almost any output signal voltage by modifying the duty cycle, thus making it similar to an analog signal. This working also explains why PWM pin is coupled with a digital pin. PWM pin is nothing but a digital pin with added circuitry to provide PWM functionality on the edge device. The device's datasheet will contain information about which pins have PWM functionality. On the pinout diagram, they are usually denoted by a tilde or the wave symbol. Now that we know how a PWM pin works and how to identify it on the pinout diagram, let's understand why we need it in the first place. Why not connect the external device directly to an analog pin? The reason is that many digital systems, like microcontrollers, cannot directly output analog signals. They would need a digital-to-analog converter, or DAC, which would increase cost and the size of an edge device, both of which are highly undesirable. PWM, on the other hand, offers a flexible way to simulate an analog output using digital means. This makes PWM particularly useful in situations where you need to control the power for devices that cannot easily be controlled by analog signals, such as LEDs and motors. Finally, let's look at PWM's applications. You can use PWM for a variety of applications, like controlling the brightness of LEDs, the speed of motors, or even the temperature in heating elements. By adjusting the duty cycle, you can control how much power these devices consume over time, which can be crucial for battery-operated edge devices in AI applications. And that is all for PWM. If you want to learn more, I will add links to some resources related to the PWM in the resources section. In the next video, we will talk about analog-to-digital converters, or ADCs. See you there. Welcome again, everyone. In this video, we're going to explore analog-to-digital converters, or ADCs, a supercritical component in edge devices. An ADC is a device that converts analog signals into a digital signal, which your computer or microcontroller can then process. Think of it as translating a smoothly varying temperature reading into a format that your digital thermostat can understand and act upon. Key to understanding ADCs is the concept of resolution. The resolution of an ADC tells us how finely it can divide the input voltage range into different levels. For instance, a 10-bit ADC divides the voltage into 2 to the power of 10, or 1024 unique levels. As you will see shortly, higher the resolution, the better the analog-to-digital conversion. This resolution, along with the resolution of the sensor, impacts the precision of your digital readings. And you will see this shortly when we look at an example. Coming to the working of an ADC, it is actually pretty straightforward. First, the resolution or the number of bits and the reference voltage are used to calculate the step size using the formula shown. Once the step size is known, in the next step, the input voltage received from the sensor is compared to the step size and simply assigned a unique digital code. Let's see how this works in practice. For an Arduino Nano, the reference voltage is 3.3 volts, and the ADC resolution is 12-bit, according to the datasheet. Using the formula, our step size, therefore, comes out to be approximately 0.8 millivolts. And so, any input sensor voltage between 0 and 0.8 millivolts will be assigned the digital code 00000000000, or 12 zeros. A voltage between 0.8 millivolts and 1.6 millivolts would be assigned the code 0000000000001, or 11 zeros and a 1, and so on. Neat, isn't it? We stated a little bit earlier that higher the resolution, the better. Now that we understand the working of an ADC, let's see why that's the case. Taking our current example, any value between 0.8 millivolts and 1.6 millivolts will be given a unique digital code. But that's a wide range. The same digital code would be generated whether the input sensor voltage was 0.85 millivolts or 1.55 millivolts. When this digital code is converted back to a value to be used in the code or for making machine learning predictions, it will lead to loss of accuracy as the computer won't know the difference. That is, it wouldn't know whether the initial value was 0.85 millivolts or 1.55 millivolts. Now, if we were to increase the number of bits, the n in the formula, so that the step size became 0.1 millivolts, then in that case, only values between 0.8 millivolts and 0.9 millivolts would have a unique code, and on converting back to a value, the error in judgment would be much lesser. Let's now include the sensor resolution in this example. If the resolution of a temperature sensor was 0.25, it would take readings like 10.25, 10.5, and so on. That is, any temperature value between 10.25 and 10.5 would be assigned one of these values. Let's also say that 10.25 corresponds to 1.55 millivolts. So, if the actual reading was 10.37 degrees, it would first be converted to 10.25 degrees, then to 1.55 millivolts, and then to a digital signal using the ADC. This digital signal, when converted back, could have a value much different from the actual value of 10.37. To summarize, the translation of an analog sensor value to digital value using ADCs, though not perfect, is still highly precise and allows devices in edge computing, like wearables and smart devices, to efficiently process real-world data and make smart decisions quickly and locally. Hope you enjoyed this video. In the next few videos, we will look at the different communication protocols that are used by external devices to communicate with the edge device. See you there! Hello, and welcome again. In this video, we will look at communication protocols, understand why we need them, and explore their different types and their advantages and disadvantages at a broader level. First, let's start with the why. Why were communication protocols designed? In edge computing, devices like sensors, microcontrollers, or MCUs, and other embedded systems need to exchange data effectively. Protocols were developed as a set of rules to enable this communication seamlessly and universally. There are two main types of communication protocols: parallel and serial. Parallel protocols allow multiple data bits, often 8, 16, or more, to be transmitted simultaneously using multiple wires. This method is incredibly fast due to the concurrent data transfer. However, parallel protocols, despite their speed, have some drawbacks. Firstly, they require more physical space for wiring, making them less suitable for compact embedded devices where simplicity and cost-effectiveness are key. More wires also mean higher manufacturing costs and potential for interference and signal degradation over long distances. In contrast, serial protocols transfer data bit by bit over 1 to 4 wires and are thus more adaptable to smaller, integrated systems typical in edge applications. The key advantage of serial protocols is their simplicity. They require fewer wires, which reduces the complexity and the cost of the hardware. They are also more effective over longer distances, where parallel transmission can suffer from timing issues and crosstalk. The main disadvantage of serial protocols: speed. Since data is sent bit by bit, serial transmission can be slower than parallel protocols, which might be a concern in applications requiring very high data rates. Serial protocols come in two types: synchronous and asynchronous. Synchronous serial communication uses a clock signal to synchronize the timing between the sender and the receiver. This ensures that both the devices are aligned on timing when sending and receiving data. This is efficient, but requires both systems to maintain precise timing, which adds to the complexity. In contrast, asynchronous serial communication doesn't require a clock signal. Devices agree on data rate and format beforehand, but are free to send data in chunks separated by stop and start bits. While this reduces complexity, asynchronous transmission is typically slower and less efficient than its synchronous counterpart. In summary, while parallel protocols are fast, their physical demands make them less ideal for modern, compact edge systems compared to the more streamlined serial protocols. Between the different serial protocols, synchronous serial protocols are faster and more reliable for real-time applications, while asynchronous protocols are more flexible and simpler to implement, making them well-suited for basic input-output operations in edge devices. In the next video, we will look at UART, an asynchronous serial protocol, and discuss its features, its working, and its wiring. See you there. Welcome to another video in this Edge AI Masterclass. In this video, we will look into one of the fundamental building blocks of device communication in edge computing, the UART serial protocol. We will start by looking at the protocol and some of the related terminology, and then go into its working and the wiring. So let's dive in. UART, or Universal Asynchronous Receiver Transmitter, is an asynchronous serial communication protocol. This means that, unlike parallel communication, which sends multiple bits at once, UART sends data sequentially, one bit at a time. Also, since the communication is asynchronous, there is no clock to synchronize the data sent and received, and it uses special bits to let the receiver know that data is being sent. We will look into this soon, but let's go over a few terms first. Data is sent from the sender device to the receiver device in packets. Each packet contains the data bits, the synchronization bits, and the parity bit. Data bits are typically 5 to 9 bits and represent the actual data. Then there are synchronization bits, which include 1 start bit and 1 to 2 stop bits, and these are on either side of the data bits to frame the data packet. The third and final type of bit is the parity bit, which is an optional bit for error checking and added after data bits. Another term to understand is the baud rate. This is the rate at which information is transmitted, and it is usually measured in bits per second, or BPS. The baud rate values usually range from anywhere between 9,600 to 115,200. The flexibility in the values of these parameters, whether it be the data bit size or the baud rate, makes this protocol highly flexible and configurable, with the only caveat being that the two devices should agree upon and use the same parameter values. Some of the use cases for this protocol are the GPS module, the Bluetooth module, the serial liquid crystal displays or LCDs that you use to display information, and the communication between your embedded device and your computer when you attach it to transfer your code. All these communications use the UART protocol. With this understanding under our belt, now let's look at how UART actually sends data. Broadly speaking, the process can be divided into 4 steps. In the first step, the transmission starts by changing the data line from 1 to 0. Or in other words, it starts when a start bit with a value of 0 is sent on the line. Once the start bit has been sent to let the receiver know that a data transmission is underway, in the second step, the actual data is sent in either the least significant bit, or LSB mode, which is the default setting, or the most significant bit mode, or the MSB mode. For example, let's say that you wanted to send capital P over the line. Capital P's ASCII value is 80 in decimal, and the binary value is 0101 followed by 4 zeros. Now, just like the decimal system, where the least significant digit is the rightmost one as it represents 10 to the power 0, similarly for binary, it is also the rightmost as it represents 2 to the power 0. And so, with the LSB mode, the rightmost bit is sent first, then the second value on the right, and so on. And so the data sent is 4 zeros followed by 1010. If it was MSB, the data would be sent from left to right. Once the data has been sent, next comes the parity bit, which is an optional bit added for error checking. It also has 2 modes, the even mode and the odd mode. The parity bit is calculated by adding the data bits. In our example, for the binary value of P, there are 2 ones, and so the sum is 2. In even mode, if the sum of the values is even, the parity bit is set to 0. If the sum was odd, the bit would be set as 1. In the odd mode, the values are reversed. Finally, in step 4, after the data and/or the parity bit has been sent, a stop bit with value 1 is sent to signal the end of packet transmission. And that is how a UART protocol works. Let's now look at the wiring, which is pretty straightforward as well. There are 3 wires including ground. The RX stands for receiver and the TX for transmitter. As can be seen, in the UART setup, the TX pin of one device is connected to the RX pin of the second device, and vice versa. So if device 1 wants to send data, it uses the orange line, and if device 2 wants to send data, it uses the green line. If the second device is, say, an LCD screen, then it will not be sending any data back And in that case, the second TXRX connection, the green line, can be skipped. Finally, the ground is connected, which completes the circuit and ensures signals are correctly referenced. And that wraps up our basic overview of UART in edge devices. If you would like to learn more, we will add some links in the resources section. In the next video, we will look at protocol number 2, the SPI protocol. See you there. Hello everyone, welcome. In this video, we will look at another important serial protocol, namely the Serial Peripheral Interface, or the SPI. So let's get started. SPI is a synchronous serial communication protocol that allows multiple devices to communicate in a connector peripheral system. Like we saw in the previous video, serial interfaces transmit data bit by bit, which simplifies the wiring. Also, since SPI is a synchronous protocol, it has separate data and clock lines to synchronize data transfer between devices. This makes SPI highly reliable. Let's look at some terminology related to SPI now. The one which is common with the UART protocol is the bit order, and which can either be LSB or least significant bit first, or MSB or most significant bit first. If you recall, LSB just means that the data is transferred from rightmost bit to the left bit, and MSB means it is transferred from the leftmost bit to the right bit. Another important term is the data mode, and this refers to the direction of the clock's oscillating signal. If the signal is going from low to high, it is known as the rising mode, and if it is moving from high to low, it is known as the falling mode. Don't worry if it doesn't make sense now. We will look at it again when we discuss the working of SPI. Lastly, there's clock divider, which adjusts the clock frequency used in data transmission by a factor usually between 2 and 128. For example, if the clock speed is 16 megahertz and you use a clock divider value of 8, then the clock speed, and thus the data transfer rate, will become 16 divided by 8, or 2 megahertz. This clock divider value is used as the SPI can operate at millions of bits per second, which may be too high for some devices. To accommodate such devices, the clock divider value is used to adjust the data transfer rate. Now that we have some understanding of the SPI protocol, let's compare it to the UART protocol. Compared to UART, the SPI is faster because it supports higher throughput and doesn't require start and stop bits. It also requires a simpler hardware setup. However, SPI also requires more wires and is not as well suited for long-distance communications as UART. The SPI is used to transfer data between the controller and devices like the shift registers, sensors, the SD card, and many more. Let's take a closer look now at how SPI actually operates. In this diagram, the upper line is the clock line and the below one is the data line. The arrowheads on the clock line denote that the data mode is rising, that is, the data will be sent on the data line when the clock signal moves from low to high. During idle time, both the lines are in high state. To start the data transmission, in step 1, the controller sends an oscillating signal on the clock to the peripheral or the receiver, indicating that a transmission is about to start. In the second step, data is sent on the rising edge, in our case, in either LSB or MSB mode. Again, like before, if the data to be sent is capital P and the mode is LSB, 4 zeros followed by 1010 would be sent. Finally, once data has been sent, in step 3, both the lines go idle or prepare for the next bit. Let's now look at the wiring and see how in practical terms you might connect two devices using SPI. For an SPI transfer, 4 wires are needed. The SCK, or the serial clock, is the clock line. PICO and POCI are the data lines. PICO stands for Peripheral In Controller Out and sends data from the controller to the peripheral. POCI stands for Peripheral Out Controller In, and it is the opposite. It is used when the peripheral wants to reply back to the controller. Lastly, the CS, or Chip Select line, is a line used by the controller to let a specific peripheral device know that the data will be sent to it. Finally, remember that the controller controls the clock and the Chip Select line, whether the data transfer happens on the PICO or the POCI line. If you would like to get into more detail about the SPI protocol, we will add a few links in the resources section for you. In the next video, we will wrap up this mini section on input-output and the communication protocols by looking at another serial protocol called the I2C. See you there. Welcome back. In this video, we will look at a very popular communication protocol known as the I2C serial protocol. So let's dive in. I2C, or I2C as it is also known, stands for Inter-Integrated Circuit, and it is a popular protocol for synchronous serial data transfer between multiple external devices. I2C was designed to take the best from both the UART and the SPI protocols. Like the UART, I2C requires only 2 lines to send and receive data, making the hardware setup simpler and more cost-effective. Like the SPI, the I2C also has a simpler software setup along with a simpler hardware setup and high data transfer rates. While I2C offers great flexibility in its ability to connect to multiple devices over the same 2 wires, it can be slower compared to the SPI and slightly more complex in large networks as compared to the UART. Some popular applications of I2C are sensors and actuators. Let's now look at how the I2C protocol operates. This can be broadly divided into 5 steps. In the diagram, the upper line is the serial data line, or the SDA, and the lower line is the serial clock line, or the SCL. Also, as you can see, the complete data packet is made up of 2 parts, the address frame and the data frame. The communication starts in step 1, when the controller leaves the SCL high and pulls SDA low, indicating to the peripherals that a data transfer is about to begin. In the second step, the controller sends the address of the device it wishes to communicate with in MSB mode, followed by a bit indicating whether it wants to read or write data. This address frame is 9 bits, with 7 bits for the address and the 8th bit for the read or write indication. A 1 denotes a read or receive operation, and a 0 on the bit indicates a write or send operation. In the third step, the targeted device acknowledges the communication by sending back an ACK signal, if the address was correct, or if it was able to parse the data, by sending a low signal or 0 on the ACK bit, which is the 9th bit. If it was unable to receive or parse, a high signal or 1 is sent on the data line. Note that the acknowledgement bit is sent for both the address and the data frame. With the acknowledgement done, in step 4, the actual data transfer happens. The data frame 2 is 9 bits with 8 bits for the actual data and the 9th bit for the acknowledgement. Once the data has been transmitted, in the final step, the controller sends a stop signal by pulling the SCL line high, followed by the SDA line, marking the end of the transmission. Finally, let's look at the wiring and see how 2 controllers can connect to 2 peripherals using I2C. As shown, both the SDA and SCL lines are shared among all the devices. Controllers and peripherals are wired in parallel, allowing seamless communication. Note that controllers communicate with the peripherals, but not directly with each other. Like before, also note that while each device on the I2C bus can either send or receive data, only the controller controls the clock, thereby establishing a clear controller-peripheral relationship among the devices. And that wraps up our overview of the different input-outputs and the serial protocols. With this knowledge, you should be able to read any datasheet with ease and choose the appropriate edge devices and peripherals for your application. In the next mini-section, we will look at the different sensors, understand how they work, and then explore some real-life scenarios where they could be used. It should be a fun section, and I am super excited. If you are too, take a quick break and then join me there. See you soon. Hello, everyone, and welcome back. In this and the next few videos, we're going to dive into the fascinating world of sensors, particularly focusing on what they are and how they can be utilized in edge machine learning systems. Let's start by understanding what a sensor is. Simply speaking, a sensor is a device that collects data about its surroundings. This data could be temperature or pressure readings, proximity to an object, or anything really these days. Sensors are essential components in various applications, from smartphones and smart glasses to industrial machinery. Now, sensors can mainly be classified in 2 ways. They can be classified based on their functionality, like reading temperature and humidity data, detecting gases and chemicals, or measuring the force being applied on it. Another way to classify sensors is to do it based on their output signal, which can be analog and digital. Analog sensors, like thermistors, produce a continuous output signal that varies proportionally to changes in the physical phenomenon they measure. Digital sensors, on the other hand, like digital temperature sensors, produce a discrete output in the form of digital signals or data. When selecting a sensor for your application, there are several key factors to consider. The first is the resolution. This is the smallest detectable increment of a sensor's output. For instance, common resolutions for temperature sensors might be 0.1 degrees Celsius. And so such a temperature sensor could give an output like 21.3 degrees Celsius, but not an output like 21.35. This higher resolution, if needed, would most probably come at a higher price. And so think deeply about what your application requirements are, and then choose your sensor resolution based on that. The second factor to consider is the amperage or current requirement. Sensors, like any other device, require current to operate, and this typically ranges from 4 to 20 milliampere. Certain high-performance sensors might need more, or energy-efficient models might need less. The third factor to consider is the response time. This refers to how quickly a sensor can provide an output after sensing an input. Fast response sensors are crucial in applications where rapid changes occur, such as in automotive airbag systems. Similarly, advanced sensors in some scientific instruments might consume more power but provide highly accurate data rapidly, compared to general-purpose sensors with slower response times. In general, most sensors provide a response in milliseconds, though some sensors like gas sensors may have a response time in seconds or minutes. In conclusion, understanding the types of sensors and their key selection criteria such as resolution, amperage requirement, and response time is fundamental in designing systems for edge AI applications. Knowing this will ensure that the right sensor is chosen for the right application, balancing performance, efficiency, and cost. In the next few videos, we will explore different sensors, their working, and their application use cases in the real world. See you there. Hello and welcome, everyone. In this video, we will be looking at our first sensor, the vision sensor. Let's start by understanding what a vision sensor is. Simply put, it's a device equipped with the ability to detect objects in its field of view, and then convert this information into a digital format. Think of it as the eyes for your machine. There are several different types of vision sensors. Some are classified based on the type of image they capture. This could range from basic image capture like color and grayscale, to advanced versions which use infrared, thermal imaging, and even multispectral imaging to see beyond what the human eye can perceive. Another specification to classify a vision sensor on is the resolution, which provides information on the clarity and detail of the image and is measured in pixels. A common resolution is 640 into 480 pixels, and higher resolutions provide even greater details. Now, the fun part. Let's explore how these sensors are and can be used in the real world. We have discussed the first few applications mentioned in the slide here in previous videos, so let's go over them quickly here. In transportation, they are used in self-driving cars, in parking management, and in ensuring that traffic rules are being followed. In manufacturing, they play a pivotal role in automating quality checks. In retail, they help with inventory management by reading barcodes, analyzing customer buying patterns, and in customer interactions through self-checkout counters. Safety and security systems rely on them for surveillance to capture any suspicious activity, and for simple everyday tasks like helping people when they get stuck in an elevator. In wildlife monitoring, they are used to collect data on animals to understand their eating, sleeping, and migratory patterns, and to then design appropriate conservation programs. In sports, they can be used for athlete performance assessment, for generating real-time analytics, and for creating automated refereeing and scoring systems. One application that we haven't covered is climate change, but it is pretty straightforward as well. In the climate change domain, we could use vision cameras to detect forest fires. An edge device with vision, temperature, and gas sensors could be installed at multiple locations inside the forest. If the vision sensor detected a smoke or a fire, it could be confirmed using readings from the other sensors, and an alert could be sent to the local fire department and the emergency response team. This timely intimation could prevent the fire from spreading and dumping millions of tons of carbon into the atmosphere. And there you have it. Whether it's enhancing security, boosting efficiency, or protecting wildlife, you can use vision sensors to build state-of-the-art edge applications that can change the world. In the next video, we will take a look at the temperature sensor. See you there. Hello, and welcome back. In this video, we will look at the temperature sensor, which, like the vision sensor, has wide-ranging applications in the real world. But before we dive into the applications, let's first start by understanding a bit more about it. A temperature sensor is a device that detects the temperature of the environment it is in, and then converts this data into information that a computer can process. Temperature sensors come in a variety of forms, like the thermistors, thermocouples, and semiconductor-based sensors. Out of these, the semiconductor-based temperature sensors, like the one shown in the image, are the most popular due to their reliability and accuracy. In simple terms, semiconductor-based sensors work by measuring changes in the resistance of a semiconductor material due to temperature variations. As the temperature changes, the resistance of the material alters accordingly, which is then measured and converted into a temperature reading. When choosing a temperature sensor, there are a few key specifications to consider. These include minimum and maximum measurable temperatures, sensitivity, and accuracy. For example, if you were to try to use a room temperature sensor, which is built for temperatures, let's say from -5 to 45 degrees Celsius, for industrial applications where the temperature can go up to hundreds of degrees, it would be pretty useless, right? Sensitivity, also known as the resolution, refers to the minimum reading that a sensor can read. Like we discussed before, if the resolution of a temperature sensor was 0.1 degrees, the sensor would be able to show a temperature of 25.1, but not 25.15. Accuracy, of course, is also important. If the actual ambient temperature was 25 degrees, you would want to understand what that would be shown as in the reading. When building an application, would that be shown as 25 or as 24.8, 24.9, 25.1, or 25.2 degrees Celsius? Let's talk about applications now. Temperature sensors have vast applications. They are crucial in HVAC systems to monitor ambient air temperatures in homes, offices, shopping malls, cars, and aircrafts. Car and aircrafts, in fact, have another set of temperature sensors. Cars have sensors that measure the engine temperature and send an alert when it is overheating. Aircraft, similarly, use temperature sensors to check engine temperatures, fuel line temperatures, power and other equipment temperatures, etc., to ensure that all systems are in order when they are cruising at 40,000 feet. In factories, these sensors prevent overheating of critical equipment, maintaining efficiency, and ensuring safety. They are also used in home appliances. Some popular appliances which use temperature sensors are refrigerators, air conditioners, rice cookers, and curd makers. And that is all for this video. In the next video, we will look at radiation sensors, which have some pretty interesting applications as well. So see you there. Hello, everyone. Welcome to another video in the Edge AI Masterclass. In this video, we will be looking at radiation sensors, which, as the name suggests, help in detecting radiation in the environment. So let's explore how these sensors work, and then look at some of their applications. Simply put, radiation sensors detect radiation. This radiation can be of different types. It could be alpha, beta, or gamma rays, or solar, or ultraviolet radiation, and so on. The working of radiation sensors really depends upon the radiation they are meant to detect. Some are gas-based, and these detect radiation by measuring the current produced when the gases are ionized by the radiation. Others are solid-state or semiconductor-based, and these absorb the energy in the radiation to generate electrical charge. The more the radiation that is absorbed, the more charge they generate, which can then be measured and analyzed. When choosing a radiation sensor, apart from the type of radiation, some other parameters to consider are its response time, its radiation type sensitivity, and its overall durability. Each specification can greatly influence the sensor's effectiveness in different environments. Now let's look at where these sensors can be deployed. With all this talk about radiation, nuclear reactors, where electricity is produced through the nuclear fission process, is a no-brainer. Nuclear reactors use these sensors to ensure that the nuclear fission process is under control and that the environment is safe for people working in the vicinity of the reactor. Another use case of this sensor, and an interesting one, is solar farms. Since these sensors can also detect solar radiation and ultraviolet rays, they can be deployed in solar farms to ensure that the solar panels are always directly facing the sun. As the sun moves from east to west during the day, these solar panels could also be rotated slowly throughout the day to make sure they are always in line with the sun. The decision to move the solar panels and the degree of rotation could be based on the readings from these radiation sensors. An edge computing or an edge ML product that accomplishes this would have a direct impact on the ROI or the return on investment of these solar farms, and thus be in high demand in South Asia, the Middle East, and Northern Africa, where new solar farms are being installed every day. Another interesting use case of radiation sensor is in medical equipment, such as in-beam PET scanners, which are used in the detection of cancer and some other chronic diseases. While all precautions that are possible are taken, the use of these sensors in these devices could add an extra layer of safety and ensure that only the right amount of dosage is being administered to the patient. And that is for this video on radiation sensors. In the next video, we will look at proximity sensors. See you there. Welcome back. In this video, we'll uncover what proximity sensors are, explore their types, understand their working principles, look at their key specifications, and discuss some exciting real-life applications. So, let's get started. A proximity sensor is a device that detects the presence of nearby objects without any physical contact. Proximity sensors come in various types. Optical sensors use light, ultrasonic sensors use sound waves, capacitive sensors detect changes in electrical fields, and capacitance and inductive sensors detect changes in magnetic field. Each type has its specific use depending on the environment and the nature of the object being detected. For example, inductive sensors are usually used to detect ferrous metals, though some can also detect other metals and metal alloys like aluminum, copper, and brass. Let's now look at their working. An optical or ultrasonic sensor works by emitting light or sound waves and then measuring the time it takes for these waves to return after hitting an object. This time measurement can then be used to calculate the object's distance or proximity. Capacitive and inductive sensors, on the other hand, detect the changes in their electric and magnetic field respectively and use that to detect the presence of an object. The first key specification to consider when choosing a proximity sensor is the type of sensor like optical, ultrasonic, capacitive, etc. And this depends upon the object to be detected and the working environment. Other specifications include the maximum measurement distance and the minimum and maximum operating temperatures. Now let's explore some applications. In manufacturing, proximity sensors can help automate production lines by detecting the presence or absence of parts. This knowledge can then be used to decide whether the next operation should be performed or not. For instance, on a packaging conveyor line, if packaging material was missing, the line could be moved forward one more step. If not, the packaging machine could be instructed to place the product inside the package and close and seal the lid. Another super popular use case is the checking of liquid levels and the presence of caps in bottles and containers. Let's say you have a wine bottling factory. You could use one proximity sensor to make sure that the bottle is exactly beneath the filling nozzle. Another proximity sensor could be used to make sure that the beverage is filled to the maximum level in the bottle. And then finally, another proximity sensor could be used to check whether the cap had been placed on the bottle or not. If the cap was metallic, an inductive proximity sensor could be used. In retail, these sensors can help manage inventory by detecting when products are taken from the shelves and alerting the staff in charge of stocking. In transportation, they enhance safety by detecting obstacles around vehicles. The parking sensors in your car are most probably ultrasonic proximity sensors. Proximity sensors are also used heavily in self-driving cars to detect objects and other cars. We earlier talked about automatic parking fee payment and highway toll payment using RFID readers and vision sensors or cameras. For them to work smoothly, the car should usually be at a certain distance from these devices. Proximity sensors can ensure that the car is in the right position. And that is it for an overview of proximity sensors. Hope you enjoyed this video. In the next video, we will take a look at pressure sensors. See you there. Hello everyone, welcome back. In this video, we are going to be focusing on the pressure sensor. Let's explore how these incredible devices work and their practical applications in our daily lives. A pressure sensor is a device that detects pressure and converts it into an electrical signal. Common types of pressure sensors include capacitive, piezoelectric, and strain gauge sensors. Capacitive sensors measure changes in electrical capacitance caused by the movement of a diaphragm, which can then be calibrated to provide a pressure reading. Piezoelectric sensors, on the other hand, generate voltage from the mechanical stress applied to certain materials like ceramic or quartz. Strain gauges measure pressure through the change in resistance of a conductor such as silicon when pressure is applied. When choosing a pressure sensor, key specifications include the type of sensor, whether capacitive, inductive, piezoelectric, or strain gauge or others, its pressure range, the maximum pressure tolerated, the resolution, and the accuracy. These specifications determine the sensor's suitability for different environments and tasks. So, where can we use these sensors? Pressure sensors are extremely versatile and have applications across multiple domains. In aerospace, pressure sensors are used primarily for monitoring the cabin pressure. They are also used for measuring the plane's altitude in some cases, as there is a direct relation between the altitude and the barometric pressure or the pressure of the atmosphere. In automotive systems, pressure sensors are used for tire pressure management, for detecting faulty hydraulic brakes, in engines to optimize the fuel-air mixture, and in cabins to detect collisions and deploy airbags. In Level 3 self-driving cars, pressure sensors are used to ensure that the driver's hands are always on the steering wheel, ready to take control if needed. They are also used extensively in air purifiers, air conditioners, and HVAC or heating, ventilation, and air conditioning systems to regulate airflow for climate control and to detect clogged filters by measuring the pressure difference between incoming and outgoing air. Finally, let's also talk about their use case in the healthcare sector. In the medical domain, they are used in ventilators to monitor the oxygen pressure and to ensure that the right air or oxygen mix is being supplied to patients. In spirometry devices, they are used to measure lung capacity of patients. They are also used in automated drug delivery system to ensure that the right amount of dosage is given to patients at the right time of the day. And that was a brief overview of pressure sensors, their working, and their application. In the next video, we will look at photoelectric sensors. See you there. Welcome, everyone. In this video, we're going to explore another fascinating component used quite frequently in industrial automation and robotics, the photoelectric sensor. So let's dive in right away. A photoelectric sensor is a device that detects the presence of nearby objects through changes in the light signal that it sends out into the environment. It captures these changes in light and converts them into an electrical output signal. The photoelectric sensor consists of two parts: a transmitter or an emitter, which emits light usually from a laser or a light-emitting diode, and the receiver, which receives the light and converts it into an electric signal. Receivers are usually photoconductive cells whose resistance decreases as more light hits them, or photovoltaic cells which generate voltage depending upon the intensity of light that hits them. There are typically three main types of photoelectric sensors. The first is the through-beam sensors, which have separate transmitters and receivers installed on opposite sides facing each other. The transmitter emits a beam of light, and if any object blocks this beam, the receiver detects the change. The second type are the diffuse sensors, where the transmitter and receiver are housed together, and when an object moves past the sensor, it reflects light back, letting the sensor know that something has passed through. They are the easiest to install, though they may be susceptible to dusty environments, which may reflect light back, and certain object textures, which may not reflect enough light back. The third and final one are the retroreflective sensors, which have a structure similar to diffuse sensors, in the sense that the transmitter and receiver are housed together, but they use a reflector like a mirror to bounce the light back from the transmitter to the receiver. When an object comes between the mirror and the sensor, the missing or low-intensity signal is detected and information sent back to the controller. They have higher accuracies than the diffuse sensor and are easier to install than the through-beam sensor, and thus have varied applications. They are especially useful in applications where the objects are fast-moving. Let's now look at the key specifications. The first one is the detection type, where depending upon the application, you may choose between through-beam, diffuse, or retroreflective sensors. The next parameter is the sensor range, and which, due to the way they work, is usually longer for the through-beam sensor and shorter for the diffuse sensor. Finally, the two specifications, which are important for all sensors, the resolution and the response time, should always be kept in mind when selecting a sensor. The response time can especially be crucial for high-speed operations. Let's now explore a few applications of the photoelectric sensor. In manufacturing, they can be used to count the number of objects coming off a conveyor belt, ensure that no parts are missing on the conveyor belt, or to make sure that the correct order of parts are flowing on the conveyor. For example, let's say you have an automation project for a Toyota manufacturing plant, which produces Corolla, Camry, and Prius. Let's also say that the demand is 1:1:3, or out of every 5 cars, 1 should be Corolla, 1 should be Camry, and 3 should be Prius, and in that order. Since these 3 cars have different engine and body parts, photoelectric sensors placed strategically can be used to identify the height or width of these different parts and ensure that the right car is being manufactured. Similarly, in warehousing and supply chain, these sensors could be used to sort parcels, with larger parcels being moved to the left where a large robot puts them on pallets, and smaller parcels being moved to the right, where they are picked up by a smaller robot or a warehouse employee. Photoelectric sensors are also popular in non-industrial settings, with one easy-to-see example being the automatic doors in buses, metros, and elevators. And that is all for this super long video on photoelectric sensors. Hope you had fun. In the next video, we will take a look at motion sensors. See you there. Welcome back. In this video, we will be looking at motion sensors, their different types, and some of their super interesting applications. So, if you are ready, let's get started. A motion sensor is a device that detects moving objects within a specified area, typically by emitting a signal, like an ultrasonic wave, microwave, or a radio wave, and then measuring the frequency of the reflected signal off moving objects. Any change in frequency would signal the presence of a moving object. These 3 types of sensors, ultrasonic, microwave, and radio wave, are known as active sensors, as they actively send a signal into the environment and look for motion. Besides these, there are other types of motion sensors, such as passive infrared, or PIR sensors, which detect body heat of animals and humans. They are called passive, as no energy is emitted from the sensor. Let's now explore the key specifications to check for when choosing a motion sensor. When selecting a sensor, consider its type, whether PIR or an ultrasonic, microwave, or radio sensor, its range, and the environment it will be used in. For instance, PIR sensors are great for low-energy applications like home automation. Let's now look at these and some other applications of motion sensors in a little more detail. A big use case for motion sensors is in building and home automation. The automatic opening of doors in retail and commercial buildings is usually achieved by the application of motion sensors. For home automation, imagine a smart home with a smart security device installed at the entrance. As soon as a motion is detected on the motion sensor, the vision sensor is turned on. The vision sensor checks if the person at the door is a resident of the house, and if so, opens the front entrance door. Other motion sensors inside the house turn on lights, fans, and air conditioners automatically as you walk through a room, and switch them off if there is no motion in the room for, let's say, 2 minutes, enhancing energy efficiency and convenience. When the house is empty, these motion sensors turn into a security system that alerts you if and when there's an unexpected movement in the house. Similar safety, security, and automation systems can be set up in factories as well. If someone goes too near a blast furnace in a steel factory or too near a hazardous chemical in a chemical factory, motion sensor can detect movements and sound an alarm. If someone tries to break in during the night, again, an alarm can go off, and the security team can be notified in real time. In fact, we are going to build something similar for our final project at the end of this course. Another application is in autonomous systems and robotics. Industrial robots are usually big and bulky and work with high precision and speed. To prevent people from going too near and getting hurt, a perimeter can be set up with motion sensors. As soon as a motion is detected, the robot can be put in standby mode or switched off, preventing possible injury. In fact, as we move towards a world with home robots where robots and humans cohabitate side by side, such a mechanism could be set up in these autonomous systems as well. And that is all for this video. In the next video, we will look at humidity sensors. See you there. Hello and welcome back. In this video, we will be focusing on humidity sensors. If you are a foodie or if you enjoy gardening, you will especially enjoy this video. So without further ado, let's begin. As you can see on your screen, this is what a typical humidity sensor looks like. A humidity sensor is a device that detects the amount of water vapor in the air, also known as humidity. These sensors are vital in various applications, which we'll touch upon in a moment. So, how does this sensor work? Well, most humidity sensors operate using a hygroscopic material that absorbs moisture. When the moisture level changes, it impacts the material's electrical properties, such as its resistance or capacitance, which is then converted into an electrical signal that the sensor passes through to the controller. There are several types of humidity sensors, including capacitive, resistive, and thermal conductivity types. Each has its own method of sensing moisture, but the capacitive sensors are most common due to their accuracy and responsiveness. When choosing a humidity sensor for your application, the key specifications to look for are accuracy, response time, and minimum and maximum operating temperature. Taking a close look at these will ensure that the sensor fits your specific needs. So, where are these sensors used? Well, humidity sensors have found applications in multiple domains. They are used in HVAC systems and home appliances like air humidifiers and air conditioners to ensure that your living environment is comfortable. They are an integral part of land and airborne weather stations to assess climatic conditions and to forecast rains. In the healthcare domain, they are used in medical equipments like ventilators and incubators to ensure that the air is slightly warm and humid and thus comfortable for breathing, for patients and newborns. In cars, they are used to control the cabin climate and to prevent the windshield from fogging. In the food processing industry, especially industrial bakeries, they are used for monitoring the humidity to guarantee the best rise for bread dough. What good would be a pastry if it isn't nice and light and flaky, right? Coming back, in the hydroponic and indoor farming space, to ensure fast germination and propagation of seeds and seedlings, a warm and moist environment is needed. Humidity sensors help ensure that the climate is just perfect for them. And finally, in places where precision scientific experiments and processes are performed like R&D labs at technology firms and universities and semiconductor fabrication plants, these sensors are used to keep the humidity levels in check so that the various instruments can make precise measurements without too much calibration. And that is all for this video on humidity sensors. In the next video, we will look at gas sensors, which have some pretty interesting applications as well. See you there. Welcome to another video in the Edge AI Masterclass, where we are exploring the different type of sensors. In this video, we will look at an often overlooked but super interesting device, namely the gas sensor. So let's get started. A gas sensor is a device that detects the presence of gases in an enclosed space or area, often as part of a safety system. How does it work? Well, one common type of gas sensor is the heated metal oxide sensor. This type of sensor operates by heating a metal oxide film that results in the release of electrons. In a regular non-gas atmosphere, these electrons react with oxygen, leaving little to no free electrons. But In the presence of a gas, and thus in the absence of oxygen, more free electrons are available, resulting in a higher flow of current, which can be measured and converted to an output signal. When choosing a gas sensor, it's vital to pay attention to certain specifications. These include the type of sensor, which would depend upon the gas or gases to be measured, measurement range, and the response time. Most gas sensors come with an MQ code. For instance, MQ2 are used for detecting LNG and smoke, MQ3 for alcohol or ethanol, and MQ7 for carbon monoxide. By the way, if you are wondering about the mesh on the sensor, that is added to the sensor to prevent dust from entering and to prevent inflammable gases from catching fire. Real-life applications for the gas sensor are vast and varied. In manufacturing environments, it is used for monitoring chemical emissions for safety and compliance. In HVA systems, they ensure air quality by continuously monitoring and selectively engaging air purifier systems when the quality drops below a certain threshold. They are also used actively by firefighters and the emergency response teams during fires to detect gases, strategize, and create evacuation plans. In homes, gas and smoke sensors are used to intimate the residents and the fire department of a leak or a smoke. In fact, since gas sensors have relatively higher response times, sometimes in seconds or minutes, a good place to put them, at least in the kitchen, would be to put them right at the stove level. This small adjustment could prevent many more fires. Coming back, in cars, they could be used to detect carbon monoxide and other toxic gases and automatically roll down the windows and cut down the engine. Since governments around the world are spending a mini fortune to build smart cities these days, let's also look at some smart city applications. In wastewater pipes, gas sensors could be used to automatically detect high levels of toxic and inflammable gases, and automatically open additional release valves to disperse these gases to the upper air. Similarly, in confined spaces, like underground shelters, malls, metro stations, and even in mines, gas sensors could be used to detect high levels of toxic gases, so that corrective actions like opening of additional air shafts and turning on of additional air purification systems could be performed. Or the emergency response teams could be automatically notified and an evacuation of the space could be initiated, depending upon the severity of the situation. And finally, to protect city residents from the toxic air from forest and farm fires, air purification towers could automatically be turned on using signals received from gas and particle sensors. And that is all for this video and this mini-series on the different types of sensors. Hope you enjoyed this series. Do let us know in the Q&A section if you did. Also, let us know which idea did you like best and which sensor has the most varied and interesting applications. Finally, let us know some of your Edge ML application ideas, which using one or more sensors and machine learning solve a customer pain point. In the next video, we will look at the things to consider when selecting an edge device for an application. See you there. Welcome again, everyone. One of the first things to do when building an application is choosing the right physical components that will collect and process the data for us. In the last few videos, we looked at a few different sensors and how to choose the right one for our use case. In this video, let's dive into how to choose the right edge device for our projects. When choosing an edge device for your application, there are several important factors you'll need to consider. Unlike centralized systems, edge computing pushes processing closer to data sources, drastically reducing latency and significantly improving real-time decision-making. This makes thinking about compute power extremely important. More powerful processors are generally needed for more complex algorithms. However, powerful processors can increase costs and energy consumption. So, choosing the right processor or microcontroller is important. An example of this is computer vision algorithms, like object detection, image segmentation, and video analysis algorithms. These are super popular and have tons of real-world applications, but generally require more compute. This is changing fast, though, as new algorithms which have high precision but low compute requirements are coming up fast. Next things to consider are memory and storage. More of these let your device handle larger models and more data. More memory allows for smoother operation when handling multiple tasks or larger data sets. But remember, accessing this memory might be slower than you'd expect in some lower-cost devices. Also, as before, it's important to strike a balance, as higher memory might increase costs and limit device compactness. Sensors integrated within the device can directly influence what applications you can support. They can streamline your product design, as well as considerably quicken your device assembly time during production stage. For instance, a device for fall detection or Alzheimer's freezing of gait or fog application with a built-in accelerometer would not only be super easy to build, but also highly practical due to its small size and weight. Another consideration when deciding on an edge device is the number and type of pins. We discussed them in detail in a previous video. The number and type of pins decides how many additional sensors or other external devices you can connect. If your project is complex and needs multiple external components, make sure that your edge device has sufficient pins. Power requirements is also an important criterion. If your device needs to operate in a remote area without constant power supply, optimizing for low power consumption is key. Another thing to note is that the external power supply numbers should match the power numbers of the edge device. In a similar vein, the edge device's current supply to input-output pins should match the sensors and external components' current requirements for the application to work smoothly and without errors. Size of the device matters too, as smaller devices work better in tighter spaces. For instance, if the size of the smartwatch or the smart glasses was too big or they were too heavy, there wouldn't be many takers for them. Now, would they? Finally, let's also discuss cost. Cost is something that your customer will always consider when assessing your product and its usefulness. Proper cost planning is important, especially if your project involves deploying hundreds of devices. This might seem straightforward, but finding a device that fits your budget, your technical and physical space constraints, and meets quality standards can be challenging, especially when deploying multiple units in field applications. And that is all for this video. I hope this overview helps you understand how to select an edge device tailored to your application's particular needs. In the next few videos, we will take a look at a few popular edge devices that you can use in your application. See you there. Welcome to another video in the Edge AI Masterclass. In this video, we will explore the capabilities of the Arduino Nano 33 BLE Sense, a compact and powerful edge device, perfect for beginners and pros alike. For computer vision applications, you can pair it with an OV7670 or a 7675 camera module using jumper wires. Coming to the specifications, the Arduino Nano 33 BLE Sense is equipped with an ARM Cortex-M4 processor, running at 64 MHz. It features 256 kilobyte of SRAM and 1 megabyte of flash storage, balancing efficiency with sufficient space for small to medium-sized projects. This device is also sensor-rich. It includes a 9-axis inertial measurement unit, or IMU, a barometer or a pressure sensor, humidity, temperature, proximity, light, and gesture sensors, and even a microphone. These features open up a myriad of application possibilities. The camera's resolution is 0.3 megapixels. The Nano has a power requirement of 3.3 volts and an extremely small form factor at 43.16 millimeters by 17.76 millimeters. At a total cost of around $41 for the device and the camera combined, with $35 for the device and $6 for the camera, it offers an affordable entry into the edge computing space. And so whether you're a hobbyist looking to experiment or a developer developing professional solutions, this device packs tons of features into a small, cost-effective package that can be useful for all. The Arduino Nano 33 supports Bluetooth Low Energy for connectivity, making it ideal for IoT projects. It operates robustly between -40 degrees Celsius to 85 degrees Celsius, ensuring reliability in diverse environments. So, apart from the upper reaches of Canada, Siberia, and the Antarctica, it can operate on almost any place on Earth. Another advantage of Arduino Nano is its compatibility with MicroPython, a mini version of Python, which is one of the easiest coding languages around for writing the application code. We will look at MicroPython in detail in a later part of the course. We have discussed applications in quite a bit of detail, so I won't go over them again here. But do note that Arduino Nano 33 has enough firepower for most typical edge AI applications like home and industrial automation. With the camera module in place, it can also do some basic image recognition tasks, like checking periodically if the pressure valve on the gas pipeline is leaking or not, or the LED for power surge on an electricity dashboard is turned on or off, or for even monitoring patients in a hospital to see if they are doing okay. And that is all for this simple yet highly versatile device called the Arduino Nano 33. In the next video, we will look at Arduino Nicla Vision, a device built specifically for computer vision tasks. See you there. Welcome back. In this video, we will look at the Arduino Nicla Vision, a powerful edge device with an inbuilt camera designed especially for computer vision tasks. So let's dive right in and explore some of its features and potential applications. The Nicla Vision is equipped with dual-core ARM Cortex microcontrollers, an M7 running at 480 MHz, and an M4 running at 240 MHz, making it capable of handling complex computations that happen inside computer vision algorithms. It has an inbuilt 2 MB of flash memory for storing code and 1 MB of RAM for executing tasks, and another 16 MB flash storage for storing machine learning models, for example. What makes the Nicla Vision stand out are its sensor capabilities. It includes a 2-megapixel camera, a 6-axis IMU that can do real-time motion detection and indoor navigation, a distance sensor, and a microphone. This makes it perfect for gathering a wide range of data right from the device for tasks like object detection and robotic manipulation. It has a small form size of roughly 22.85 by 22.85 millimeters and requires roughly 105 milliampere of current during image capture. This translates to over 400 hours or over 16 days of battery time with a 42,800 milliampere hour power bank. I will add a link to the power bank in the resources section if you are interested. We haven't tried the battery ourselves, but found a few US YouTubers who do camping videos say good things about it. If you do try it, let us all in the community know how it went. Coming back, the device is priced at $115 at the time of making of this video. For connectivity, it supports both Wi-Fi and Bluetooth Low Energy, allowing it to easily communicate with other devices or the internet to send or receive data. Like the Arduino Nano, it too can work in most places on this planet and supports MicroPython. Let's now look at some applications. With its 2-megapixel camera and high compute power, it can easily be used for most object detection applications, whether it be asset tracking applications in manufacturing and retail, or safety and security applications, or predictive maintenance applications in the renewable sector or wildlife conservation. It can do it all. Another interesting application could be in hydroponic automation, where it could be used to provide data on crop harvesting time, as well as to detect weed and pests in crops. And that is all for the Arduino Nicla Vision. In the next video, we will look at one of Nicla Vision's closest competitors, the OpenMV Cam H7 Plus. See you there. Hello everyone and welcome again. In this video, we are going to look at the OpenMV Cam H7 Plus, a powerful edge device tailored specifically for computer vision tasks, and a close competitor to the Arduino Nicla Vision. So let's dive straight in and see how the two devices compare. The OpenMV Cam H7 is built around a robust ARM Cortex M7 processor, which operates at up to 480 MHz. It includes 33 MB of total memory, 32 MB of flash storage, and uses a 5-megapixel camera as its primary sensor. This compact device measures only 45 by 36 by 29 millimeters and draws about 240 milliampere of power, meaning it can run for nearly 178 hours or over a week on a 42,800 milliampere hour power bank. Also, despite its power and big camera, it's quite affordable at around $85. One of its biggest drawbacks is its lack of connectivity. While just like most other edge devices, you can connect it to another microcontroller or an external Wi-Fi shield, it at present has no connectivity module built in. Like others, it supports MicroPython scripting. The device operates reliably in temperatures from -20 degrees Celsius to 70 degrees Celsius. which, though enough for most environments, is still slightly less than what several Arduino devices offer. Now let's move on to practical applications. As compared to the Arduino NICLA the OpenMV Cam H7 Plus has a bigger camera, more memory and storage, though less compute power, and is cheaper by around $30. This makes it best suited for asset tracking and safety and security applications, where you may need bigger models with higher precision. Also, since it is cheaper, deploying tens and hundreds of these devices at large power and energy installations for these tracking and security applications could be significantly cheaper. Ultimately, though, choosing the right device would really depend upon your customer's requirements and your application design. So, think things through. And that wraps up our introduction to the OpenMV Cam H7 Plus. In the next video, we will look at another popular and powerful edge machine learning platform for computer vision, the Arduino Portenta H7 with the Vision Shield. See you there. Hello and welcome again. In this video, we will look at another popular edge machine learning platform from Arduino, the Portenta H7, shown in the top left. If you are wondering why an Arduino again, the reason for this is that just like Python, the Arduino and Raspberry, another manufacturer of edge devices that we will explore later, have a strong community and support system. This means that in case you get stuck somewhere during your application build process, there are ample resources available online to help you out. Coming back, for computer vision tasks, the Portenta H7 can be combined with the Vision Shield, which is shown in the bottom right. Let's explore them now in a little more detail. The Arduino Portenta H7 is a powerful microcontroller designed for demanding applications. Like the NICLA Vision, it features a dual-core setup with a 240 MHz ARM Cortex-M4 and a 480 MHz Cortex-M7. Alongside, it also houses a GPU, the Chrome ART accelerator. This setup means even faster processing and the ability to handle even more complex tasks efficiently. It includes 8 MB of memory and 16 MB of flash storage for your programs and data. The combined setup, along with the Vision Shield, features sensors like a 320 by 320 pixel camera, a temperature sensor, and 2 microphones. The combined power requirement for the setup is around 530 mAh, which translates to 81 hours or over 3 days of life on battery power. Designed for versatility, it measures only 66 mm by 25 mm, making it compact yet powerful. Perhaps one of the biggest drawbacks of the system is its combined price of around $183, $114 for the Portenta and $69 for the Vision Shield, which makes it slightly more expensive than some other options with similar computer power available in the market. Like others, it also supports Wi-Fi and Bluetooth Low Energy for wireless connections, and can operate in extreme temperatures ranging from -40°C to 85°C, making it suitable for industrial environments. In terms of software, it supports both MicroPython and TensorFlow Lite. TensorFlow Lite, as the name suggests, is a lighter version of the Google's popular machine learning library, TensorFlow. When it comes to applications, the Arduino Portenta H7 can be used in the real world, not only for asset tracking, object detection, and industrial automation, many of which we have already discussed, but even for more complex and power-intensive applications like service robots for deployment in malls, schools, and hospitals. And that is all for the Arduino Portenta H7. In the next video, we will look at Raspberry Pi 5, a device which is really a computer that fits in your hands. See you there. Hello, everyone. In this video, we'll explore the powerful Raspberry Pi 5, which, although discussed along with and used as an edge device, is also sometimes called a mini computer that can fit in the palm of your hands. Let's see why. The Raspberry Pi 5 is equipped with a quad-core ARM CPU running at 2.4 GHz, ensuring swift processing speeds for demanding tasks. Whether you opt for a 4 GB or an 8 GB SD-RAM model, this device is built to handle complex computations promptly and efficiently. Comparing it with some of the earlier devices we discussed and with some budget computers, you will see clearly that these specifications are much closer to that of a computer than with an edge device. Hence, the mini computer title. Coming back, For storage, it supports PCIe 2.0 to connect to M.2 or NVMe solid-state drives, providing fast and flexible options for your project needs. All this power comes in a compact size of only 85 millimeters by 56 millimeters and with a power supply requirement of just 27 watts. Also, don't forget the price, which is between $60 and $80, depending upon your chosen memory configuration, and in the same range or lower than most edge devices. It features Wi-Fi and Bluetooth Low Energy or BLE5 for seamless connectivity. Though its operating temperature range is not specified, typical Raspberry Pi models can handle standard room temperatures well. Another reason why it is called a mini computer is because it has a proper operating system, the Raspberry Pi OS, which is a derivative of the Linux operating system. This makes this device even more unique in the edge device space. Let's talk about some real-life applications now. The Raspberry Pi 5 can do almost everything that other edge devices can do, only better. It can be used in various scenarios like asset tracking, where devices monitor and manage the location of assets in real time. In object recognition, it can identify items through cameras, useful in manufacturing, retail, transportation, security, and many other smart city applications. Furthermore, it's an ideal choice for industrial automation, enhancing efficiency and safety, and for powering autonomous land, hydro, and aerial robots, providing the brain for smart, independent machines. And that is all for Raspberry Pi 5. In the next video, we will look at what TinyML is and how it is related to edge machine learning or edge AI. See you there. Hello and welcome to this final video in the Introduction to Edge Devices section. In this video, we will explore what TinyML is and how it is related to edge machine learning or edge AI. So, let's begin. TinyML is a rapidly emerging field that stands at the crossroads of machine learning and embedded systems. It focuses on developing machine learning models that can operate on extremely low-powered devices, like microcontrollers, typically in the milliwatt range. And so, TinyML, edge machine learning, and edge AI are all terms used to describe the same broad concept. If you really had to nitpick, I would say that while doing machine learning on a Raspberry Pi would be considered edge machine learning, for it to be considered TinyML, you really would have to use one of the other microcontroller-based devices like the Arduino Nano 33 or the OpenMV Cam H7. But this is again just nitpicking, and in this course, we will use the terms interchangeably. As we have already discussed, TinyML enables intelligent decision-making directly on the device. This minimizes the need to transmit large amounts of data to the cloud, enhancing privacy and reducing latency. Launched by an alliance of industry leaders and technologists who believe in the power of AI to operate on the tiniest of devices, TinyML has a clear goal, which is to make AI accessible and feasible on small devices that are used daily. This is achieved through the optimization of machine learning algorithms that can work within the power and memory constraints of embedded devices. As one of the founding members puts it, a lot of research had been done in the last 5 to 10 years on fancy, high-end cars, referring to machine learning, but not much focus has been put on road and highway construction, referring to deployment options like the edge device. And thus, TinyML is all about deployment and using the power of machine learning where it really matters, at the edge. The work in the field is coordinated by a foundation with the same name and with members mostly in the US, Europe, and Asia. The foundation released their first white paper in February 2023 and do knowledge sharing through in-person and online talks and meetups. Supporting this mission, several industry giants have stepped in. Notable sponsors such as Edge Impulse, TensorFlow, Arduino, alongside Qualcomm and Sony, provide the necessary tools and frameworks. These companies are helping in shaping the future of TinyML by contributing their expertise and technologies to support its scalability and ease of implementation. And that is all for this video and this section on Introduction to Edge Devices. In the next section, we will look at the basics of MicroPython and see how to write code that uses these edge devices and components to perform a task. See you there.